Now it's really a great privilege to welcome tonight's speaker. Retired Vice Admiral Conrad Lautenbacher has had a very distinguished career. He's a native of Philadelphia, a graduate of the U.S. Naval Academy, class of 1964, and during his 40 years of service in the Navy, he won accolades for performance in a broad range of operational, command, and staff positions, both ashore and afloat. And his military career was marked by skilled fiscal management and significant improvement in operations. It's really hard to go through all the different things that he did in his 40 years, so I'm just giving you a very high-level approach, but obviously 40 years in the Navy is a wonderful thing. He also received his master's and his Ph.D. from Harvard University in applied mathematics. His service did not end with his retirement as a Rear Admiral. In fact, I think a lot of us really got to know him more sort of in his next series of positions. He formed his own management consulting business initially, and then he became president and CEO of the Consortium for Oceanographic Research and Education. Many of you have heard about this organization. It's a nonprofit organization that represents 100 institutions like Harbor Branch throughout the country that all is in support of basic knowledge and public education under the spectrum of ocean sciences. Many of you know about our National Ocean Science Bowl, which we just had here a few weeks ago. That was all established by Corps. And then from 2001 to 2008, the Admiral served as Undersecretary of Commerce for Oceans and Atmosphere and the 8th Administrator of NOAA, the National Oceanic and Atmospheric Administration. Many of our speakers refer to NOAA, and that's always one question. If they don't say what it means, they say, what is NOAA? And now you're going to see somebody who ran NOAA for the better part of the last decade. As the NOAA Administrator, he did a lot of things, including spearheading the first ever Earth Observation Summit, which hosted ministerial level representation from several dozen of the world's nations in Washington in 2003. I think you'll hear tonight some of the outcome of that effort in his talk. More recently, the Admiral is Vice President at CSC Corporation and President of Antarctic Research Support, LLC, working to expand expertise to support national research and presence in the polar regions. And still, among all his other activities, he's an active member of the board of the Georgia Aquarium. Many of you know about the Georgia Aquarium. If you ever go to Atlanta, you need to go. So as you know, climate change is both an emerging issue for society and a frequent theme in our lectures the past couple of years. And tonight, Admiral Lautenbacher will bring a national and international perspective on this issue and technology involved in his lecture on global Earth observation and climate change.
Thank you for coming this evening. It's a really great pleasure to be here. This is a wonderful institute and organization that supported ocean science for a long time. I've been a big fan of Harbor Branch, and I'm really pleased to see that you are fans of Harbor Branch as well. So thank you for coming this evening. As mentioned, I want to talk about, they asked me to talk about climate change, and I'm not going to tell you what to believe about climate change, and I'm going to cover that in just a second. But I want to do a couple of things tonight, and I'm going to get started by just moving on here, I think. Let's see if we can do this. There we go. So that's the agenda. I want to set the context a little bit, talk about what we know. I said on the title what we don't know, but how do you know what you don't know? So I don't like that conundrum. So let me tell you what I think's missing, because you can kind of figure out what we don't have that we'd like to have. So what's missing is a better. I want to emphasize the complexity and the totality of Earth systems, because this is not an easy problem. And I want to talk to you about why global Earth observation is necessary and what progress has been made if we're ever going to get to the end of this conundrum and get what I would call a really good answer for what to do with climate change. I want to talk about how that relates to the environment. I want to talk about the future a little bit. So that's what I'm going to try to convince you to do tonight. Now, context setting. You heard my background on from the official bio, which is so I'd like just tell you. I think when you listen to somebody, you ought to know where they're coming from. So let me tell you where I'm coming from, so you know what's influenced me throughout my whole life. Basically, I've been a naval officer for a long time, so I've been in the Navy. I am a science aficionado. I have worked, I have a background in applied mathematics and in engineering and atmospheric physical dynamics, fluid mechanics sense. My thesis was on tsunami wave run-up many years ago, so I have been actually in demand in the last 2 or 3 years because we've actually had tsunamis. For 40 years, we had none, and nobody cared what my thesis was about. Now, all of a sudden, it's important. It's the way things go. So that's my background. In the Navy, I've been a financial manager, so I'm very interested in money. My last job was running the Navy $100 billion budget and force structure and how many ships should we have, how many people, et cetera. So I've been a financial manager and operations analyst in the Navy. And then you've heard I've been the head of NOAA for the last, basically, the 7 years till the end of the Bush administration. And Jane Lubchenco is now the Obama head of NOAA, and a fine lady and a great scientist. And I wish her great success. So that's my background, where I'm coming from. Science aficionado, naval officer. And I got to say that I am an environmentalist, and I don't know anybody that's really not an environmentalist. I've never met anyone, no matter where you come from, that wants to trash their environment. Whatever your political persuasion is, people like to live in a decent place. And so I don't want you to associate the word environmentalist with something negative in your mind. I hate this term, global warming and climate change. And the one question that always used to bug me that I got in my 7 or so years, you know, in the political agenda in Washington was, do you believe in global warming? Do you believe in global warming? Well, first of all, global warming is associated, people say global warming, they think, well, humans have done something to change our climate, and so this is really bad. So global warming, even though it's just a term to say the Earth is warming, turns out to be a political catchphrase that as soon as you get involved in that, you immediately are in trouble with whoever's asking the question. Climate change I like a little better because it's a more scientific term. If you go over, and I will show you that climate's gone up and down over the centuries and the millennia, et cetera. So I want you to focus more on climate change and the global warming. I don't believe in global warming, but I believe in my faith. There's a lot of things I believe in, but you should look at the science, and you should be able to either prove it or disprove it in your mind, or accept what you read and what you've determined from looking at real information, real facts, and make up your mind. Whether you believe, and I hate the word believe, it's whether you think it's supportable or not. But believing in it is not helpful. We would like to have science to back this up. And the next thing there is the science is settled. The science is never settled. Science is never settled. I hate that phrase too, and I hope you don't think science is settled. We need to continue investing in science and investigation. Today's world is technologically oriented. Without what we've learned using the scientific method, which is a way to observe and actually find out the truth of what's happening in the world around us, we wouldn't be living here today. Everything we have in terms of our society that allows 7 billion people to live on this earth is based on our scientific ability to manage and harness technology. Complexity, it's a very complex subject. It's not easy. You can't get an easy answer on climate change itself and a simple policy answer to it. So I hope that you come away with and I'm going to try to show that to you. Science and public policy, I guess the other thing, I'm just going through my pet peeves so you'll understand what they are, because I've spent 7 years living with this. Science and public policy. Scientists should be scientists, and politicians should be politicians. That's what I believe. And so I've tried to be very careful as the head of NOAA not to be a politician, because I was running a science agency. And I think if you want to have credibility as a scientist, you need to do your best to explain all sides of an issue. Here it goes, and this was bad. Oh, I got it back before I had to type the password in. All right. That means I spent too long on that slide is what that means, ladies and gentlemen. So Science and public policy, they should be separate. And I firmly believe in that. If a scientist wants to be a politician, he should get up and say, I'm a politician, I believe in global warming, and you ought to do this. And that's fine with me. I don't really care about that. But he's designated himself, he or she, as a person with a political agenda. So I think it doesn't do science any good or our credibility in the system to be able to determine what's going on when people mix those roles or get them confused in their mind. Climatology and meteorology. How many people watch the evening weather? I bet there's a lot of people here that come to this who are interested in the evening weather. Well, the evening weather comes from meteorologists. Meteorologists are generally skeptical of climate scientists. And I can tell you, having to operate an organization with both in them, climatologists have a different view of looking at things than meteorologists. And so you need to be, and I put a little footnote there from a New York Times article, and it talked about I will call it friendly tension that goes on between weather people who like to see, observe what they see and really make something out of it, and climatologists who are going to tell you, in many cases, what's happening 100 years from now, which based on models. So there's a pet peeve there as well. Okay, let's go on. Okay. And I'm going to let you read that a little bit, and I'm going to tell you what we know. We have temperature records, and I'm going to tell you about ClimateGate in a minute and whether the temperature records are any good. But we have temperature records. We've watched the ice melt. I mean, these are facts. You can see them. You can see the temperature records show it's going up. You can watch ecosystem changes. You can watch the bark beetle attack all of the pine trees in the west. You can watch the change of early blooming of plant life and those sorts of things. You can see the temperatures in the ocean change, and some of the fish move from the colder to the following the temperature further north. So it's not, the Earth is warming right now. There's no, you would have to accept that, I think, okay? Severe weather, we know there's severe weather, but quite frankly, you can't associate one severe weather event statistically with a climate event. You can say, well, some of the models say the weather will get more severe, and look at that, we just had a hurricane, okay? But we've had hurricanes for years. So you got to be careful about, but we do have severe weather, and we've had maybe more, but we've been able to observe more too. We also have an international panel for climate change that comes together every few years, makes a big assessment, and it's a synthesis of the best science that we have around the world. And they're in trouble right now because somebody made a mistake on when the Himalayan glaciers will melt. And they put a very early date into it. So we have two events that are undercutting climate scientists today. This what I would call catching errors in the IPCC report, International Report on Climate Science. And we have the fussing with the data, this ClimateGate incident. And that is probably one of the hardest things to deal with, is the fact that the data that we have is not what I would call climate quality data, because it's obtained from weather records, and sometimes in many years past people put the temperature behind the tree, sometimes they put it in front of the tree, sometimes they put it in the city, sometimes they put it in the country. Those are simple examples, but the fact is that you have temperature records that people have adjusted to try to eliminate some of these differences in the records, because when we're talking climate change, we are talking temperature changes of hundredths of a degree every year. Now, how many people trust the thermometer in your oven? Hey, it can be a degree off here, 5 degrees there. It's, so temperature records are important. We're talking about changes that, are fit between my fingers per year. So people have worked hard to to modify the data sets. And so I don't want you to get excited one way or the other about ClimateGate, but that's what it's about essentially. So what's missing? We do not have any comprehensive global climate observing systems. We don't have the instruments in place steadily 24/7 that give the information. We have some experimental satellites and instruments that do that, but we are today working hard to get a system that will give us what I would call the quality of data needed to deal with climate change. And the accuracy of the historical records. You have to realize that thermometers and regular recording started in 1870 or mid-1800s. You go back beyond that, you've got tree rings, you've got ice cores, you've got sediment cores. So there's a certain amount of uncertainty in working with those records. You haven't had time to verify models. Now, you can tell whether the weather forecaster at night had a good forecast a couple of days from now, because you'll go out and say, he said it was going to rain and it was clear. You can tell, and our models are getting better and better. And having been in charge of the Weather Service, there's facts to show that. You may not believe it, but there are facts to show that we're getting better at predicting weather and more accurate in predicting it. We can't verify these climate models with the future. We can go back and say, well, we made it work so it's accurate in 1935 or it worked for 1950, but until it plays out, I don't know. Anybody can get up and criticize it, and anybody can say, no, it's accurate. So time is not on our side in this case. Computing capacity, to build a model that's sufficiently complex to take in all the issues would take many orders of magnitude of computing capability than we have today. So the models, in my view, they're great advancements over what we had, but they are still in I would call an infancy. Remember, we've been doing weather models for decades. We have been doing climate models for 10 really complex climate models for, I don't know, 10, 20 years at the most. And indirect effects, there's a lot of indirect effects. There's the Earth's orbit, there's the sun's radiation, there's the effect of clouds. There's many things that are not in these models directly. And the worst one is the bottom line is we haven't had an objective forum free from political grandstanding. So every time you say global warming, everybody says, do you believe in it? And well, if you say if you believe in it, and you're on that side, that's good. If you say, well, I don't believe in it, you're a baddie, or vice versa, depending on if you're a skeptic or not. So those are kind of the big things that I think are interesting to keep up. Now, I want to show you just a few slides that actually come from the skeptic side, and I don't know whether I have an audience tonight of skeptics or an audience of believers, and I don't really, and I don't mean to make fun of it. I'm just trying to make a point, because I think there's ample evidence on all sides. I've got 3 slides here that are courtesy of Burt Rutan. He's got them on the net if you want to watch. He's got a bigger presentation. Burt Rutan, first of all, is not a climate scientist. He's an engineer. And his claim, he claims that he's a guy that can interpret data. And he can. He's built some of the most inventive airplanes that have circled the Earth, high altitude. He's an enormously talented engineer and smart person. So he picked out a few things that kind of stretch his credibility. And just, I want you to, when people start talking about greenhouse gases, what you see up there, you see that big block up there is all the greenhouse gases, which comprise 2% of the whole atmosphere. Then you have 3.62%, 3% of that, 3 to 4% of the greenhouse gases are CO2. So only 3% of the greenhouse gases are CO2. And then you've got 3.4% of that are caused by human activity. So he looks at that and says, come on, you're telling me that we're doing something nasty to the environment. Now, there's an answer to that. If you go on the side and you look at the radiation physics of how radiative heat transfer moves through the atmosphere, you can make a case that little bit of, supposedly little bit of carbon dioxide makes a difference. So I'm going to tell you there's answers to both sides of this, but that's an interesting, it's just an interesting fact that's worthwhile thinking about. So we're not breathing a whole lot of carbon dioxide out there, all right? And here's what the things looked like over many, many years. And the point I make here is the cycles. This is cycles. You know, we have a daily cycle. So this goes back 600 million years, okay? This blue line is the temperature, and you can see what the Earth's average temperature was over here. And then this is the carbon dioxide line. And we are in a condition right now in the last 600 million years where temperature and carbon dioxide have been at their lowest levels since 300 million years ago. Now, that doesn't prove that humans are not changing the climate today by adding stuff to the atmosphere. But it shows you that the climate does work in cycles, and it's very complex, and there's huge uncertainty. See, this is all uncertainty. this huge block right here through all these areas back here. So that's another thing Burt Rutan cites, just to give you what the skeptic is saying. And now this is probably one of the most controversial issues with the skeptics in terms of the temperature record. What you see here is an IPCC report from 1990 or so, 91, 90. They put one out then, and then they put one out in 2001, 10 years later. And there was a time called the Medieval Warm Period and the Little Ice Age, and these were temperature records supposedly not adjusted very well. Well, by the time they got here, people had adjusted this so much that it disappeared. All right, now if you're a scientist, I mean, you know, all of us have been in the lab trying to verify Newton's laws, et cetera. I mean, you're really interested in having accurate data. So there's a lot of interest in how people actually made these adjustments to originally discovered and written and published data. And so that bothers Burt Rutan either. And this is the famous hockey stick brief. And of course, this is only back to the year 1000. This is just the little end of that last graph that I showed you. So all I'm asking you to do is keep things in perspective. I'm not telling you, I do believe that we are causing problems with our environment. The humans are doing that. So I will start by telling you, I think that's an issue. I accept, I don't say I believe in it, I accept the information that I have seen that that is the case. But you need to know, when you listen to these arguments, there are pros and cons on both sides of this. And it's going to be a long time before we settle these arguments. Okay, now I want to give you an example on complexity. I'll try to run through this fast, but it's really an interesting one. I was at a, what I do for CSC is I am the president of a joint venture that's working to get the Antarctic support contract. Remember, Antarctica used to be run by the Navy. It is for 50 years it's been demilitarized and run by a treaty which the U.S. has supported and honored and involved with to make it immune from any conflict, so that it's demilitarized. It's supposed to be totally preserved and from any human effects, and it's open for basically research. And that contract now is managed by the National Science Foundation because it's a science issue. Antarctica has a big role to play with climate, and I'm going to show you that in a second. So what I do is I've been working on the Antarctic, and so I'm going to connect you with how the Antarctic works with the climate. And this is just one simple example of the complexity. And I got a lot of these things from a conference I attended, I don't know, a month or so ago, from listening and watching a few presentations and getting some information from some of the PIs, the primary investigators that are working in Antarctica now to solve some of these climate issues. And what I want to show you is how connected our Earth systems is. So I'm going to take you through a series of slides that go to chlorofluorohydrocarbons, or those are the refrigerants that we have banned that have created the ozone hole. I think everybody is, you know, we've had to change that because we have the Montreal Treaty. We are now using chemicals which are much less destructive to the stratospheric ozone layer. But I want to connect that and show you how it connects to sea level rise in one small area. In the meantime, connect it from the oceans to the atmosphere, to the chemistry, to the ice melting, and it's a very interesting little example here. So let's move on to that. Okay, now, for those of you that may not follow the next set of slides, just memorize that. Okay, and I'm going to go through quickly because we're not going to dwell on each one, but anthropogenic means man-made, human-generated. Women did it too, so I'm not a sexist in that regard. Okay, it's all of us. Created an Antarctic ozone hole. That has actually decreased the Antarctic atmospheric temperature because, remember, ozone is a greenhouse gas. So the less ozone you have, the more you're going to have a decrease in temperature because it's not capping the sun's radiation from escaping. So actually, it's decreased the temperature. That has then, because the temperature on the outside is warming, where there are greenhouse gases, it's increased the pressure gradient, which then increases the atmospheric winds, the conservation of momentum moves those winds closer to the Antarctic continent. There's a current underneath it called the Antarctic Circumpolar Current. basically starts moving in because it's wind-driven, the oceans and the atmosphere connected, and then it's getting so close. This is the hypothesis now. This is not proven. The hypothesis is that it's now melting the West Antarctica ice sheet in an increased manner because of this, basically, ozone. And when you do that, remember that's ice that's now, a lot of it's been on land, so once it melts and goes into the ocean, remember the Arctic doesn't increase sea level rise, the Arctic is already floating, so it's just like an ice cube in your drink. It's not going anywhere, it just melts. This ice will increase sea level rise. So let's step through that because I think it's an interesting deal. Okay, so we start with ozone. I like this picture. I had to use it. So anyway, this is me and Dr. Susan Solomon, who is one of the early pioneers and gets a lot of the credit for the chemistry and researching the ozone hole in Antarctica. And she's worked on this for a couple of decades. And she's a NOAA scientist working at the Earth Research and Science Laboratory in Boulder. And I happened to be with her at the South Pole for the opening of the new South Pole Station, which is this huge thing. Actually goes on for 2 blocks down this direction. It's enormous. This is the geographic South Pole, and that's the start. And it was only 18 below that day, so it was not too bad. I took we took our masks off. Okay. All right, so ozone hole, person who discovered it and got many, and it was also the author of the IPCC report, the physical report, the first edition, not the one that's being criticized for having bad typos in it, okay? Anyway, that's the Earth Sciences Laboratory, the gas chemistry laboratory at the South Pole that NOAA runs. As you see one part of it, I'm in this picture. This was the NOAA staff. NOAA has 2 people here in the winter and generally 4 or 5 people. There happened to be 6 of us that day at the South Pole because it was a big day of celebration. And you can see here they measure every conceivable gas you can measure. This is one of the base stations. You see all their test standard gases here that they measure against close to 200 different gases in the atmosphere. NOAA measures it at 4 places on the Earth. Point Barrow, Mauna Loa in Hawaii, and Samoa out in a remote place, and then the South Pole, because those places are as far from human influences as possible and give you baseline atmospheric background, if you want to call it. Okay, so there's that. Now this is what the ozone hole looks like, and I'm not going to go through all these charts, but I got them from various resources. This is actually a NOAA chart, comes from a satellite. And it shows you basically that the depletion of ozone is that's the Antarctic continent, this little thing that looks like a pear hanging from a tree. That's the South America, here's Australia, and here's Africa, just so you get your orientation. This is not the normal way you look at the continent. I'll show you that in a minute. But you can see substantial ozone hole. This is 2009. That's what it looks like in the whole column, so you can't really detect it. This is from a satellite, so it gets the whole air column. So there's the hole. Okay, now you look at the temperature trends from the same satellite system, and you can see this is through 2004, but still it goes on. Here's the South Pole. This is East Antarctica, and this is West Antarctica. You can see West Antarctica is a lot smaller, and it's covering islands. East Antarctica sits on a big continent, if you want to call it that, above sea level, and you can see the temperature getting colder here, and it's warming out here. So that means, and I don't have a chart of the next one, that means that you're going to have increased winds closer to the continent, and this is a map of ice loss rates. Now this is how Antarctica is normally shown. For those, how many in the audience know what the convention is for showing Antarctica? Since north is always at the top of a chart, north is every direction from the South Pole, right? Okay, so a little known fact, if people look at it, it's usually oriented towards the 0 meridian or the Greenwich meridian. So people should display Antarctica like that. That's the standard way of doing it. Here's South America is off here. And Africa is off here. Anyway, this is a map of ice loss. Now, these big red blobs are huge. This little one is 10 gigatons per year of ice being melted. So it's a lot of ice. Of course, the Earth is a big place, so don't get bamboozled by large numbers. But if you look over here, Now, all these little letters are the names of glaciers and ice sheets and that sort of thing. You look over here, it's very little ice being lost, some of it in the ocean, but generally speaking, it's actually gaining in the Ross Sea, which is where McMurdo is. This is the U.S. Staging base right here. But huge amounts of ice are being lost right here. This is we're calling this the Pine Island Glacier, and you can see that you can't. I don't even know what I won't even begin to tell you what the number is. But these ice sheets are melting fast. So this is why some people will say Antarctica is cooling. Some people will say the Antarctic is warming. What I'm showing you, it's doing both. So now the ocean. Let's connect the ocean to the ice. These are 3 references, and these slides are courtesy of Bob Binshadler, who is a PI for NASA, is doing some work down there. And these are 3 references that tell you about dramatic thinning of the ice Antarctic sheet. The West Warm Ocean is eroding the West Antarctic sheet. So that's stuff you can read in journals listed over there. And this is something called the Antarctic Circumpolar Current. And it, let's see how we're doing here. Okay. So it travels in this direction, and these are different levels of that current. And the innermost level, as you can see now, it is right at the edge right here. So his theory, and it's a theory, remember, because it's not been proven, is that this current is undermining basically this ice sheet and melting, but it doesn't stop there. So he wants to prove that, and that's just a blown up picture of how close it is to that ice sheet. So he wants to investigate that ice sheet. All right. Now you got to look at the fact of how that works. And Antarctica is a place where there's something called upwelling. This is where meridional overturning of the current. And so this is looking at a cross section. This is, let's see, I'm not doing with this right. Okay, this is the continent. And then he just drew this in here. This is like the continent. The continent's a little bit below sea level at this point. This is an ice sheet, and this is where it kind of breaks off. And then this is a diagram from a book. It's cold, deep water is what it's called, and these are temperatures. You can see it's really cold here. This cold, deep water is not all that cold because it's a couple degrees centigrade above freezing. So that water comes up here and then circulates back out again. The so-called Ekman drift is pushing the ice out to sea, and then it's gradually breaking off from this ice sheet. Okay, let's see. There we go. And this is a little bit more accurate deal with a hypothesis. Here comes this cold, deep water. It comes up over the shelf, and it's funneled in here because there's a bathymetry, which I'll show you in a minute. It's very shallow here. Comes in, reaches the so-called grounding line, and starts melting the ice at the grounding line, which then undermines it and lets it go faster. This is a hypothesis now, okay? And then, of course, it breaks up icebergs, and away they go. And let's see. Okay, we're good. Okay, and I'm not going to dwell on this too long. There's seasonal variability. That's where you see this is the bottom of the ice sheet. Okay, and this is the top of the ice sheet, and the grounding is right there. That's where the supposed ground is. And then this fluctuation means that the ice sheet freezes in the winter, so it gets thicker, and then it gets you know, et cetera. And then this is a distance, and there's variation here, and there's variation here in the heat content. This is a heat content showing annual variation as well as this ripple in the effects of the ice as it's moving out, because remember, ice is moving and flowing in that direction. And this is the bathymetry, so you have to know how deep this is. These are places where samples have been taken. And here's Pine Island. Here's what he's going to do. Okay, right? It's right in here, right in this. I'm sorry, right there. It's right in this area. Okay, now this isn't proven. Now, how are we going to prove this? You can't pick up the ice sheet and look underneath of it. The ice, if you looked at that other chart, is like 600 meters thick. So that's a lot of ice. So he's mounting an expedition to drill a hole. So you're going to drill one hole in the ice, and with hot water technology, you go down and put some probes down there. Take CDT, as the oceanographers call it, the temperature conductivity. He's going to put a camera down there, and he's going to start taking, and then he's going to go further down. He's going to get the layers of water temperature, and he's got 1 point. Now, it'd be nice to have the whole system mapped. So maybe at some point we'll put an AUV down there, an autonomous underwater vehicle that can swim around and actually map all of that. And how long is this going to take? He started working on this 3 years ago, 2 years ago. They actually drilled a test hole last year, which froze up, but they had some interesting results, which with the time I'm not going to go into them. He's not going to get to do this until 2012. Now, to investigate what Antarctica does to the climate and sea level rise, it's going to take a lot of ice holes down there to make this happen. So we need global observing, and we need investment in science to be able to do this. But this is the kind of thing that's going on. And remember, for every dollar you spend on science in Antarctica, it takes $4 to keep that guy there with his drill and all of that. So it's a very expensive proposition to work there. And it's only the developed countries are really able to do that. Okay, I want to give you 5 or 10 minutes, and then we'll quit, on Earth observation. Observation's fundamental to the human species. We observe everything all the time. You can't stop observing things. We adapt because of our observation. And we grab a raincoat when it rains, and we need the data for the economy. We need the data for our technology. Today, nations share information across national boundary. Weather satellites, spread of diseases, global seismic networks, our tsunami reporting systems. We have them. We're sharing the information. We need to do more, and we need to go to get climate involved in this. So what's been done? We have put together I don't know, 5 years ago, 2003 or so, 6 years ago now, something called GEO, a first Earth observation summit. We brought the nations together. We created a group on Earth observations, and we are building and planning a global Earth observation system of systems together with our nations. This is not a political deal. The Obama administration supports this, just as the Bush administration supports it. It doesn't get much coverage, but it is an important aspect that we need if we want to talk to people about climate change, and we want to talk to people about doing something about it. This is what we need to get the ground truth data to be able to do the science to get this out of the political arena. And it may take a few years, but if you don't do it, we're going to be making this argument, you know, for ad nauseum, and your grandchildren will be making the argument too. And I don't think they should be doing that. Okay. It's up to 80 countries are doing this. It's voluntary. It's in Geneva. The idea is to obtain a comprehensive, coordinated, sustained Earth observing systems. It's voluntary. It's outside of the UN system, but it coordinates all of the UN agencies, which is kind of interesting. At some point, it ought to be in the UN system, but it's kind of nice working outside the UN system and bringing it together. There's a 10-year plan to try to make things right, and when that 10-year plan is done, you got to build another one, because remember, science is never settled, okay? And the concept is very easy. You need the space-based, air-based, cryosphere, land-based. Cryosphere means the poles. And you need an information system, and these are the 9 benefit areas. So it's not about the science per se. It's about making science work for all of the things that we need down here: water, energy, agriculture, ecology, health, all of them. Now, I just want to give you some examples of where it works today. This is the El Nino system. This was put in internationally. Today it's supported by the US and Japan. These are all the buoys that give you the temperatures and the conditions in the water in the Pacific. We also need satellites to do it, to tell you when there's an El Nino condition. El Nino conditions correlate to climate variability over seasonal, and we can predict them 3 to 6 months in advance because we have that system. This is the tsunami warning system, which is almost global. After the Indonesian quake, we were able to get funding from the President and Congress to put in a system which warns against tele-tsunamis, as they call them, ones that are so big that they cross the ocean, and also instrument tide gauges so that we could figure out when it's hitting the coast and then make projections. Now we need a global climate observing system, and we particularly need a carbon monitoring system. If we are going to have a cap and trade system, if we're going to get internationally and tell people they've got to buy carbon credits, how are we going to enforce that, and how are we going to tell whether we're having an effect? Without this kind of system, you're not going to do it. I also might mention the water cycle is really important in this too. So sustained Earth observations are key. How much carbon do we have? How much in terms of carbon monitoring we have today? We have a nice thing called Carbon Tracker, and that's just a model over here, and it's made by the same outfit that does that did the ozone monitoring. How many places do we actually take real carbon data? This is it, the whole Earth. Those are the only places we get carbon data, and there's only really 4 stations that are baseline stations, these blue ones, 1, 2, 3, 4 that I mentioned before. Some of these others are pretty good, but they're not the kind of thing you need, and they certainly don't cover places where we really need it. As you can see, China and Russia, Africa, South America aren't covered very well. So those are places where we get data. So that little diagram is a model plus data input, but we don't have enough data. So what can we do? And this is about the environment. I think that we spend too much time talking about climate or global warming and not looking at the whole picture. And we are doing a lot of stuff to our Earth that's not making it very pleasant for ourselves and for the future. So we need to invest in all of the kinds of science, Earth sciences. We need multidisciplinary work. If I showed you anything with that example of drilling the single hole in Antarctica, it's that geophysicists need to talk to climatologists. I didn't even get into the biology of what's happening to the animal life around Antarctica, which is changing, by the way. Multidisciplinary work, Earth observation, working together. That's what building a bigger tent means. Let's get together and stop quibbling over who gets the research pot this year. Let's build an argument to get more for everyone that's doing this kind of work. Civility. I have seen so much incivility in the scientific community regarding climate change. People get wrapped up in it as a belief, we need civility, and we need civility in our political system and among our general public. We need to talk about this objectively and not make it a political grandstanding issue, which is what it turns out to me right now. We need a national climate service, and to their credit, Gary Locke announced a NOAA climate service a month and a half ago, but we don't argue a whole lot about weather. Now, you can blame it on, but you can blame it on NOAA. You know who to blame it on, right? Who do you blame bad climate predictions on? There's no belly button, folks. There's no one to go to because any researcher can get up and tell you what he thinks about climate change. You've got NASA that does some of it, the NOAA does some of it, the folks out in Denver do some of it, the universities have laboratories, and everybody loves to grandstand in research. Remember, the Weather Service takes the best research and provides you an answer that they will answer to Congress on. If you don't like what the Weather Service is doing, you call them up and you say, are you using the best model? And they have to prove it publicly. We need to do the same thing with climate, all right? And that's something that's important, and I try to make that pitch wherever I go. I think it's an important one. And building a sustainable future. And now I'm down to the end, okay? We're gonna stop in just a couple of minutes. What can we do? What can we do in this audience? We can preserve and conserve our surroundings. We can work with local community action agencies. Harbor Branch is a great place. There are ways to deal with preserving and conserving what we have so that we can at least study and find out what it really looks like and how it worked before we destroy it. Okay, we need to invest in Earth observing systems. We need to make the information freely available around the world on a continuous basis. GEO is working, but not enough people know about it yet. We need to educate the public. There's nothing like education. And science based on data, not speculation. And look at recovery projects. So those are things that we could do here to help. And I want to leave you with, I used to give this pitch to my team at NOAA because the connection in the E words are really critical. I don't know why it came out that way, but they're all E words. At the bottom, you have this thing called education. If we have people that don't know what they're doing, we're in big trouble. But on this balances this economy, the environment, and ecosystem. Now, everybody knows what the economy is because when you don't have money, it's a bad economy. So everybody knows what economy is. You go over to environment, and it usually it enrages some people, and other people dismiss it. But the environment is what we live in. The environment affects ecosystems because now you bring in the living chain, the chain of life that supports us in the ecosystem. So people really need to understand ecosystems. So you need to make this connection. Right in the middle of this is energy. Energy is what we grow and thrive and live on. Energy, the sources of our energy are causing us issues today. certainly in climate change, and they cause us issues with the atmosphere. They cause us issues with the ocean as well, because they provide pollutants that destroy the purity of where animal life lives in the oceans and the air that we breathe, and we need them both. So remembering that connection and trying to understand what it means and this is a way to think about it very quickly. All right, that's it, folks. I want to thank you for your attendance. I'm a big fan of looking for a sustainable future. I think that's where we ought to be talking. That includes climate change, that includes cleaning up the oceans, that includes being good citizens to help support the kinds of programs that will allow us to do that. And so it's for a sustainable future, and I want you to remember the complexity. It's from ozone to the oceans. It's all connected. You can't take one thing out of the so-called climate system. It's part of the Earth system of systems. Thank you very much.